Hi, my name is Craig Labovitz. I'm with now with Microsoft Research, as well as partially still at the University of Michigan. And today I'll be speaking about the problem with BGP. And for those of you who didn't already know there was a problem, we'll spend the next, I think, hour talking about more problems. This work is done jointly with some of my co-authors, and I think Abha's in the back as well. So I just threw in these two slides just during the last talk. And I think one of the interesting things, this isn't really related to my talk per se, but I just threw it in. One of the interesting things you really have to distinguish between is prefixes and routes. Prefixes have been mostly, fairly linear. But the thing that will kill us, and the thing you have to be afraid of, if you aren't afraid of prefixes, are the routes. That is the number of prefixes and the number of people from whom you hear them. And this slide just shows the bottom is actually the number of prefixes, and the top number is actually the number of routes. And as I'll explain later, especially with relation to this talk, it's the number of routes that's a scary thing. Prefixes, more memory we can handle. Routes is what will get us. So why will it get us? So this talk is really about, one of my research interests is really how well does this thing we've built, this backbone, scale when we get to thousands of BGP speakers and 80,000, 100,000, 200,000 prefixes, and how do we really provide services over this network? So there's a lot of just kind of conventional wisdom. If you read the textbooks on BGP, or if you read some of the papers people have written about path vector protocols and distance vector and why RIP is bad and evil and BGP is great, there's a lot of conventional wisdom that BGP has solved the routing table looping problem. Just RIP would count to infinity and oscillate, but the path vector and ASPath solves the problem. There's a belief, including in the Cisco FAQ, that that BGP has far better convergence properties than RIP. And it's kind of funny for me reading QoS papers. There's lots of QoS research papers, almost as many QoS papers as there are multicast research papers. And all these papers just have little taglines at the end saying, and we assume in the interdomain will rely fast restore, IP fast restore. Pretty big assumption. There's an assumption that the internet is pretty good failover when a multi-home route is switching from, say, a primary to a backup route, that this happens within seconds, maybe 30 seconds. And there's a belief that the small delay in BGP convergence and BGP route propagation is just CPU and link latency. And if we have faster CPUs and faster links and more bandwidth, the problem goes away. So this tends to be quite a bit of the conventional wisdom. Oh, one more, that more peers is better. That more peers, the more multi-homed you are, the better the failover, the more failures you can tolerate, and the better availability you can provide to your clients, customers. Well, it turns out all these are wrong, and badly wrong. And I'll spend the next 25 minutes or so hopefully convincing you why all these assumptions are flawed. So this is really the second half of the talk. At the previous NANOG, we presented just basically our measurements and experimental results. Essentially, we presented a study where we deployed probe machines at some interesting locations at May West, at other places around the net. We set up default-free peering with some 25, 30 providers. And for the last 2 years, we injected routes into the internet to see, well, how long do failures and changes take to propagate? So for about 2 years, we've injected about 150,000 or so BGP changes for autonomous system number and address space allocated to our research effort. And in this second half of the talk, we'll explain really some of the measurements and where these come from and the convergence properties of BGP. So this is just a high-level diagram. I'm kind of pointing, but I don't have the pointer offhand. That's okay, Susan. I don't need it. Well, it's okay. So we've had a probe machine at one end injecting faults. That way you can ooh and ah at the animations. Faults propagate through the internet, and we collect them and monitor them at the far end of the machine. At the same time, we're also sending out ICMP and doing, oh, wow, cool, thanks. Yeah. So injecting faults here, propagating through the internet, and measuring them at different exchange points, all NTP synchronized, measuring the rate at which BGP propagates through the internet. So
I'm now going to go just a couple slides and provide some background and a little theory, not too much, and try to explain and provide the intuition for why BGP has some difficulties. So traditional distance vector protocols, Bellman-Ford protocols like RIP, suffer things that are broadly all routing table loops. That is, if RIP didn't have redefined infinity as 16, it would quite happily count to infinity and things would increase forever. And I'll show the example in the next slide. And it is widely believed that the addition of the path vector to BGP, specifically the ASPath, has solved the routing table loop problem. So here's just a quick example with a little nifty animation of what's really happening. So we've got two ISPs, two autonomous systems, A and B. Initially, A can get to B can get to A via a metric of 2 via the link. A can get to B via 2, and B can get ASP-A can get to R via 2 plus 1 is 3. And similarly, B can get to A via, or can get to R just via the directly connected route. So what happens when R fails? Well, ISP-B kills it out of its RIP table, fails over, does junk collection, whole bit, and 30 seconds later, it will get a RIP announcement from ASP-A. ISP-B goes, great, you can get to R. I'll add 2 to it, and I'll create a new distance vector metric of 5, and I can get to R again. This is great. ISP-B then goes back to A, hey, I can get to R via 5. And of course, A replaces the route from B with 5 and adds 2 to it and gets 7, and we go on and on until we either hit 16 or infinity, whichever comes first. So there's the belief that BGP solves this type of oscillation. And basically, if you read the papers, there's kind of a victory was declared. You know, the flags were waved, we've won, we've solved, we've nailed this problem down through the maintenance of a path vector. Let's go home. And in fact, the problem is not only is not solved, but the addition of the path vector has made it not even exponentially, but factorially worse. And I'll speak about that in a few more slides. So as I mentioned, that we have this problem with counting to infinity, as I showed in the slide before. And this is really just due to lack of incomplete information, lack of synchronization, where nodes will quite happily increment metrics forever, or until 16. And RIP does the addition of the definition of 16 really does solve the counting to infinity problem for RIP. And the ASPath does solve the counting to infinity problem for BGP. And specifically, BGP is now constrained to the width of the internet, or the longest possible ASPath, or path through all of your neighbors. So the path vector does solve infinity, but as I'll show in the next few slides, it makes the bouncing problem and the routing loop problem much, 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 much worse. So let me provide an example. A couple of assumptions as we go through this example, that this is just assuming the full mesh. We're assuming constrained policies. That is, we're just defaulting. There's no fancy route maps and magic windows. We're not going to do things that Tim will talk about shortly, but constrained policies. In this example, we assume unbounded delay. Basically, there's no constraints placed on how long a BGP message has to take. So we're going to assume it can take as long as it wants and be queued and processing as long as it wants. And if you assume BGP messages can take their time, which they can, in fact, not only can they, but they do, then you can assume just about any ordering of messages such that you preserve BGP semantics, which include FIFO ordering between two peers. That is, you aren't going to reorder messages sent between ASP-A and ASP-B.
Craig, can I ask a quick question? Because you've changed this presentation significantly from the last time you talked about this stuff. Why are you assuming constrained shortest path ASPath selection algorithm as opposed to longest match, most specific prefix?
That's a good question. That this is looking at that. So there's multiple ways to do things like multi-homing, including being part of an aggregate and others.
Right. But I mean, if you get longest match on a most specific prefix, then ASPath really has no meaning. Yeah. So it's another talk talking about other ways to do multi-homing. This talk is focusing on just the same prefix. Okay.
But I think it's a very valid point that there's lots of other things that need to be looked at, and that this doesn't apply to other things. This is just very specifically looking for the same prefix.
Okay.
And again, it's typically, I think a lot of things we're looking at are some of the typical cases where people are prepending ASPaths for multi-homing or other backup path reasons. So in this, we'll start with this example. At time, here we have, again, 4 autonomous systems, all connected. AS0 initially has, let me get the pointer, a route via 3, and this is in sort of Cisco-like format. The asterisk means it's the active route. It has secondary paths, again, the B is for BGP, R via 1.3, R via 2.3, and so on. It should look fairly familiar to folks. So we show the routing tables of 3 ASs at time 0. At time 0, R goes south. Poof. What happens next? Well, AS3 happily sends out withdraws to all of its neighbors. All of its neighbors get the withdraws. They kill off their primary active routes. And before anything else happens, they will want to send out new announcements to tell folks about the new backup paths they've chosen. So AS2 quite happily sends out the new announcements. Hi, I've chosen path 203. AS0 tells its neighbors, both 1 and 2, hi, I've chosen path 013. AS1 tells everyone, hi, I've chosen path 103. Everyone got so far? I see people nodding, okay. How do you like the animations? Yeah, okay, great. This took a lot of time. The next thing that happens is 0 sees 2 routes, both of which have an ASPath through it. So 0, of course, does loop detection and happily withdraws these routes. But AS1 and AS2 get the new routes and just have now a longer ASPath from 1 and 2. In the next stage, AS0 sends out a withdrawal when it knows all of its routes no longer exist. AS1 and 2 get this withdrawal, fail over to their tertiary path, and now, in the next stage, will send quite happily announcements to each other. And boom, boom. Finally, they see the loop through each other, and we're done. So these are 4 nodes. The important thing to notice about this example is notice that we've gone from paths of length 1 to paths of length 2 to paths of length 3. That we've explored several different AS paths. And that was for 4 ASs. It gets a lot more interesting when you get into the thousands of ASs, or more likely, the 10 or 12 for all default-free peering, the major backbones with each other. So the problem with BGP is that there really and truly exists an ordering of messages such that BGP will explore every single AS path of every single length. Let me just repeat that again, because that's pretty astounding. Every AS path of every single length in the process of converging. And for those of you who are more math inclined, that means the upper bound on BGP convergence is factorial. And as computer scientists, we don't see factorial very often. We get really excited when we see factorial. Most things at best are exponential. It's really hard to design a factorial algorithm. There are very few bounds which are factorial. But factorial is a really, really big number. So let me provide some intuition about what is happening and where we strayed from RIP. And again, I take Paul's point that this, again, is just for the same prefix, and there are other ways to do multi-homing and other things. But to provide a little more intuition, that RIP is, in computer science terms, monotonically increasing. And what that means is it just goes 1, 2, 3, 4, 5, 6. You never do 4 twice. You might count all the way to 16, but you only have one stop along the way. Whereas for BGP, how many ways can you represent 4 autonomous systems? A, B, C, D. Well, it turns out quite a few. And in fact, in the worst case, you will try all of these different metrics for representing 4. RIP just does it once. BGP does it 4 factorial, which is pretty impressive. So the intuition here is really that BGP solved the RIP counting to infinity problem by making it exponentially worse. And just if you didn't believe all of that, here's a real example. This is a real, you see, I even say it's a real example, so you have to believe it. This is a real example. The first and last AS have been changed, but everything else is just pulled from our BGP logs of an unnamed provider. Let me go back. You'll notice a couple of things here. You'll notice, as we did in our earlier examples, you start off with, in steady state, we had a route. At time 0, or 10:40:35, and for those who really want to know, it's Eastern Standard Time, we withdrew the route. We then monitored all the routes we got from a single ISP off at May West. We withdrew the route in Michigan, and this is a peering session with a peer out at May West. You notice that in 30 seconds, we get a new ASPath, new ASPath, new ASPath. It grows and grows and grows and grows and grows until finally, about 10 minutes, I forget how long, can't see the time. Finally, it actually withdraws the route. But in practice, we see ASPaths of up to 19, and we see up to 22 announcements for a single withdrawal. So for those of you who believe this is just a theoretical problem, it really happens. The other interesting thing to notice about this is the 30-second interval between the different announcements. And if you just hold on to that for a second, we'll come back to that in a few more slides. So it turns out the worst case for BGP is really, really bad. In fact, it's so bad, computer scientists get really excited and see the factorial. But in practice, that doesn't happen because, even on busy days, it's hard for every message to take more than 30 seconds. Generally, BGP messages do move along within roughly 30-second bounds. But in the best case, it turns out the worst case can happen. It is a valid ordering, and you can in fact simulate this. You can take routers and playing a few games with instrumenting gate D or MRT, you can actually get this to happen with real boxes. But it turns out that this doesn't happen in practice. And what happens in practice is even a little more interesting. In practice, that the implementation of the min-route adver timer, which I'll explain in the next slide, leads to the creation of artificial rounds in BGP convergence. Again, that these rounds don't have to be there. They really are an artificial construct. And the rounds arise, as I'll show in the demo coming up, due to the delay in the discovery of mutual dependencies during BGP convergence. So what is min-route adver? For those of you who don't read the BGP spec, it's the minimum interval between successive BGP updates for a given prefix to a given peer. This was added, and Sue will correct me and others much more familiar with BGP than I. But it's really designed for two reasons. One is to allow for greater efficiency of packing updates. That is, you'd like to pack multiple routes with the same ASPath and everything rather than a single prefix per packet. So it's designed for protocol efficiency, as well as, I think, more of an afterthought as a rate throttle on the number of BGP updates. Min-route adver, at least according to the RFC, is only applied to announcements and not to withdrawals. And I say not to as I say, the RFC specifies this because most vendor implementations, or at least two major ones, don't do this. And it's applied on, at least in theory, on a prefix destination basis, but because there'd be an awful lot of memory, it's more often applied just on a per peer basis. That is, you'll delay 30 seconds before anything you send to your peer, because you don't want to keep timers on every route in your table. So what does min-route do to us in practice? Well, I'm going to go through the example I went through before, but this time illustrate where min-route adver comes into play. So again, at time 0, route R goes south. We send out our withdrawals. The withdrawals go. We send out our announcements. And as soon as we send out our announcements, we enter what we've been calling the min-route adver penalty box. Once you enter the min-route adver penalty box, you cannot leave until for 30 seconds. You're out of the game. So AS2 is in the penalty box. Can't send any announcements to its neighbors for another 30 seconds. Okay, AS1 now sends out its announcements. Enters the penalty box. AS3, AS0 sends out its announcements. And it will, come on, looking for crowd participation here. Thank you. Enter the penalty box. So we now have everyone in the penalty box. They all change their route. So while you are in min-route adver, you do receive updates, and you do in fact change your RIB, your forwarding table. You just don't make new announcements to your neighbors for 30 seconds. So what happens here in the next slide, at least in theory, min-route adver doesn't apply to withdrawals, and at least 0 would send out with a withdrawal to, there should be another arrow here too, to 2 as well. So sorry about that. But AS0 at this point sends out a withdrawal, which isn't held by the min-route adver penalty box to both of its neighbors. And AS2 and AS1 now have one route left. They both think it's a perfectly great route, perfectly valid. They're really happy with this route. It's a great route. Unfortunately, it's bogus, that they have a mutual dependency through each other. And because they're both in the min-route adver penalty box, they're not going to learn this for 30 seconds. Eventually, once the penalty box expires, you can see the penalty box expired. Penalty box expires. They'll finally exchange their updates and will finally converge. And finally, after 30 seconds or 60 seconds, we will have finally withdrawn the route. But notice that this is really an artificial delay created by the delay in learning about a loop. It's nothing to do with CPU, nothing to do with link latency, but it has everything to do with the way min-route adver is implemented on most commercial routers today. So min-route adver routes, it's really easy with a bit of hand-waving and graph theory and graph paper to show that with n autonomous systems, all full mesh, there are necessarily n-3 rounds. So the convergence time of BGP in the best case today is exactly 30 seconds times n-3. And the experimental data shows this, as I'll show at the end of the talk. So what does min-route adver do? And excuse me, my mouth is getting dry. Well, min-route adver it does do a great thing. Min-route adver does suppress a lot of those invalid states. Min-route adver is a big win. It adds basically synchronization to BGP and stops us from exploring exponential number of intermediate states, or actually factorial number of intermediate states, which is a good thing. Each round of min-route adver, each 30-second round, you explore, you increment your path by 1. You go, so it really starts to look a lot like RIP, actually. Additional messages are suppressed, so we don't explore all of those states. The delay is exactly 30 times n-3 seconds. And the rounds are really due to an ambiguity. And the ambiguity isn't necessarily bad or good. It's just that all the commercial routers today, or most of them, do receiver-side loop detection. So the problem is that if in the previous example, AS1 and AS2 knew that they were about to send a path of 102 to 1, and instead send to withdraw, things would be much different. But because they wait for the receiver to get that, they wait for that 30 seconds. And it turns out, again, that a number of vendors, for some very good reasons, have included BGP withdrawals within min-route adver, so that also delays things. So BGP with min-route adver, the time complexity, we have the state complexity of RIP, which is, I guess, a good thing. I mean, at its best, BGP performs as well as RIP, not necessarily RIP2, RIP in general. But the interesting thing about BGP is that to get BGP to perform as well as RIP in terms of convergence, we use exponentially more memory. So we've solved the path vector problem, we solved the counting to infinity problem, but in the process, in the worst case, are factorially worse. In the best case, we're only as good as RIP, and we use exponentially more memory. So, and all this goes away if major vendors would deploy sender-side loop detection. And there's even some reasons why sender-side loop detection might not be a good thing for like AS healing and other people doing strange things. But if you do sender-side loop detection, in the best case, it doesn't help the worst case. In the best case, the rounds all collapse down to 30 seconds. And BGP convergence times go from 10, 15 minutes to 30 seconds. And you can actually do this in practice and simulate it. And speaking of simulations, this just shows some simulation results for 3 things. These simulations were done using MRT, actually generating real BGP update messages and sending it to MRT, and even we did some work with GateD. So going through real BGP policy engines. The leftmost one is for unbounded delay. That is, we assume the ordering of messages can be whatever we want it to be, as long as BGP semantics are preserved. And it's kind of impressive. For 7 autonomous systems, if you've ever wondered how many BGP updates can 7 autonomous systems generate for a single withdrawal, the answer, you can go home today, is 23,000, which I think is pretty impressive. Mileage may vary. So a single withdrawal can generate, in the worst possible case, 23,000 updates and explore 1,955 different AS paths, which is pretty big. With min-route adver, this drops down considerably, both the number of states and the messages, but we do have these artificial rounds created. So 7 autonomous systems, all full meshed, will always take, if they are full mesh, 120 seconds to converge. If you make a change and do sender-side loop detection, in the best case, you converge down to a single 30 seconds and use basically a few less states but the same number of messages. So this would be a big win if vendors did it. And it turns out one major vendor with 12-point other release does do, unnamed vendor is doing sender-side loop detection. Just to convince you that this is all real, that this is getting back to the data I showed before, and having gone through the analysis, that this graph shows really 4 things. T up is basically in steady state there's no route, we do an announcement. T short is in steady state there's a really long ASPath for a given prefix. How long does it take to converge? And T long is in steady state there's a long ASPath, we announce a short ASPath. And T down is we withdraw a route. This is a cumulative percentage graph. 0 is the time we actually withdrew the route at one end of the internet. And the seconds here are the seconds it took for a cumulative percentage of these things to actually reach steady state. And by steady state, I mean no more announcements. And you see that for basically, when in steady state there's no route, and we just do an announcement, it's between really, within a minute, 60 seconds. And this 60 seconds, it turns out, is also just due to min-route adver, because min-route adver is applied to peer basis. Even this route, which in steady state doesn't exist, will capture 2 peers. And for most of the people we're monitoring are 2 ASs away from us, and hence you get the 0 to 60 seconds, or the 30 to 60 seconds. And for the withdrawals, you see the min-route adver rounds here as well, that the reason it's a curve is that the internet isn't a full mesh. And when it's not a full mesh, the ordering of messages does matter, but really it does range from 80 to up to 15 minutes in the worst case. So for those of you who believe that you can just rely on the fast IP interdomain restoral for your voice over IP, you can if you don't mind your customers waiting for 15 minutes. So it does exist. It just takes a while. You just need patient customers. I won't show this slide because I'm running tight, but essentially, as all of you know, route flaps wreak havoc with end-to-end. Loss goes up to 50%, latency is havoc, and we did end-to-end measurements as well, which do agree with the routing convergence numbers, which basically say failover. During failover, for that 15 minutes or that 5 minutes, the average isn't too bad, 3 minutes, that you do have very high loss, very high latency, and periods of unreachability. So this is all really bad news. Tim will actually speak about worse news coming up. It's not his fault. But so where do we go from here? Well, it really does help things if vendors did apply sender-side loop detection. It did not apply min-route adver to withdraws. At least one major vendor is going to do this with future releases. This does create some additional problems, and they're outside the scope of the talk. The other thing you can do is certainly more hierarchy works, that if the internet were all one, WorldCom, it's not a problem with convergence. But it's really the number of adjacent peers that's a problem here. Every additional peer you add, and again, it's not the number of prefixes, it's the number of routes. Every additional peer you add adds, today, 30 seconds to failover convergence. So it's pretty expensive. Peering is expensive. If you have hierarchy again in the internet, like the old NSFNet model, or a single backbone, you don't have the problem. And of course you could always bring back the NSFNet. But there's other things you can do too. There's a number of papers. There's things which talk about adding synchronization. But these things really arise because people are sending out new announcements before they hear from all their neighbors. And if you add synchronization to the protocol, it solves the problem. But the problem with adding more synchronization and more state to BGP is really that arguably BGP has been as successful as it is because it's a very simple, well, at least originally was a very simple protocol, but the path vector is pretty straightforward. It's simple, not a lot of complexity, not a lot of state. You really can recreate the telephone network and add more state, but it's not clear that you have the scaling benefits any longer. And there's certainly other protocol schemes which are under investigation and link state, and yeah. So that's it, and I'll take questions for I think 2 minutes. And if you could bring up the lights.
Quick, I just have a quick question. Could you argue that today there is a relative hierarchy? It may not be a single NSFNet backbone, but there certainly are some top-tier players that collectively represent that core backbone, yes?
Yeah, so if you read, if you look at the ARIN allocations, there's, I forget how many, there's thousands and thousands of ASs allocated. If you look at BoardWatch, the number of ISPs that claim to be Tier 1 ISPs, there's thousands and thousands. In practice, when you look at the BGP data and look at May East and data from May West or from default-free tables, there's really 7, 10 folks, and the data really reflects just adjacencies, full adjacencies between something between 7 and 10 providers. If all these Tier 1s really were Tier 1s, we'd be waiting hours for BGP convergence. But because we're only waiting, up to 15 minutes, it means there's only really just a handful of these, 10 or so in the core. Yeah.
So what you're saying is that unless we get a lot of default-free tables, then this problem won't happen? Because I'm noticing that on the internet today, some very large unnamed hosting houses, for instance, have literally hundreds of ASs with whom they peer, and they don't wait even 15 minutes, more or less, several tens of thousands of seconds for things to converge. So I'm wondering why that doesn't show up in the table already. I mean, why aren't we seeing it today with real data, with the real internet?
Yeah, I'd have to know more about what you're specifically seeing. All I know is what we've measured. And as Paul pointed out, that this is, particularly you care about this if you're multi-homing via ASPath prepending. If you're doing aggregation or communities or other schemes, there's other ways to do this multi-homing.
I was just going to comment in relation to that, and also into what you said in the last few slides, that the majority of the delay that you were commenting about in there, in your diagrams, results from not just additional peers, but additional peers with peering to all the other additional peers.
Yeah.
So the reason that we don't see the kind of convergence problems that were stated is because that, as stated, there are only 10 people or so who have peers with all the other possible peers.
Yeah. Okay, one last question, Randy.
Randy Bush, Bavaria. The truth is that as an ISP, we at least do not analyze how long it takes for us to see convergence on a route or propagation, etc. So what we see is CPU spikes, what we see is, we'll conduct an experiment or play a game or inject a route and go see how long it takes to get to the other end of Charlie's network. But I'm very skeptical of operators who think they don't have these problems.
Yeah, maybe we'll take questions for the entire group at the end. Oh, I'm sorry. By the way, one comment. By the way, I haven't shown what happens when you get enough messages to trigger route dampening. And that's another talk, which I'll maybe do next NANOG. So it actually gets worse, but yeah.
Hi, this is Mike Shields at the bottom of that. I noticed that in all your cases you have the case of a route R, which is withdrawn at a single point, and how long it takes to fully withdraw from the entire internet. It goes to an unbounded ASPath before doing that. But it seems to me the much more interesting case is the case where R has a second uplink, R prime, to another AS, which would then have, if it continues to be up, it's a fixed ASPath, and the R withdrawal could only draw in length to be as long as R prime before it would become no longer preferred and no longer important.
Yeah, well, it turns out that that's just an easy way to write the example. You can also convert the example, instead of AS3, convert it to R, multi-home to 3 providers, and you get the same behaviors. If that was your question, I think, that it's not necessarily just have R connected from one ISP.
I think the case of how long it takes something to go away from the internet once its only link drops is much less important than the question of how long it takes to fail over to a working path once one path goes away.
Right, and it turns out that the data is exactly the same for a sufficiently long ASPath to go to withdraw. Takes almost exactly the same time as it does to fail over from a short to a long ASPath. So it's actually in the equivalence class. So for primary to backup route is almost exactly the same as a withdrawal.
So you're saying that it can take, because it seemed to be that you were showing many steps where the ASPath could go from 2 to 12 or much longer, but if you have a second route with an ASPath link of 3, then I mean, how can it be important if the R route grows an ASPath link with the 12? All the traffic will be already flowing over R prime.
Maybe later I'll show you examples.
Okay.
Okay. Thanks.
I think we better cut the questions off. Craig, thank you.